Let me introduce our next speaker, Juhyun from QUIC. Juhyun is currently a junior in the School of Electrical Engineering at Korea University. She is doing an internship at TRI and conducting research in the field of quantum communication. Today, she will be presenting a talk titled Provably Secure and Practical Quantum Key Distribution over Long Optical Fiber, sharing insights from the paper Provably Secure and Practical Quantum Key Distribution over 307 km of optical fiber, Korzh et al. Please join me in welcoming Juhyun to the stage.
Can everyone hear me clearly?
Yes.
Okay. Hi, my name is Juhyun Song, and I'm majoring in electrical engineering at Korea University. I'm also part of QUIC, and I have strong interest in quantum communication, so I prepared today's presentation on provably secure and practical quantum key distribution over long optical fiber. In most research papers on QKD, the focus is usually on explaining the specific protocol used and detailing the experimental setup, comparing the performance metrics of the system. However, rather than focusing on experimental results and performance comparisons, I thought it would be more helpful to explain the working principle of each protocol based on my understanding from reviewing multiple papers. So my goal for today is to make it easier for you to grasp how these protocols function so that when you read related research papers in the future, you can analyze them more efficiently. Since the focus is more on understanding protocols rather than performance analysis, today's talk might feel a bit easier. So if you feel that certain parts are too basic, please let me know in the feedback survey later. So now let's get started. I guess many of you here are already familiar with QKD, quantum key distribution, but for those who might be new to this field, I'd like to first introduce what QKD is and why it is necessary. So modern cryptography heavily relies on mathematical problems that are computationally hard to solve. For example, RSA encryption is based on the difficulty of factoring large composite numbers. However, Shor's algorithm, which runs on a quantum computer, can efficiently factor large numbers, making RSA and other classical cryptographic methods vulnerable. This is why we call what we call quantum risk, the threat that quantum computers will break existing encryption schemes. To address this risk, two main approaches are being developed. One is quantum key distribution, and the other is post-quantum cryptography. QKD uses the principle of quantum mechanics to securely share encryption key. A crucial property of QKD is that any eavesdropping disturbs the quantum state, making it detectable. However, QKD requires specialized quantum hardware and dedicated quantum channels, making large-scale development challenging. It is important to note that QKD only deals with key distribution, not data encryption itself. For the PQC, despite having the word quantum in its name, PQC does not actually use quantum properties. Instead, it is purely based on the classical mathematical problems and can be implemented using traditional hardware. It relies on computational hardware assumptions that are believed to secure against quantum attacks, such as lattice-based or hash-based cryptographic schemes. Both approaches aim to secure communication in the era of quantum computing, but QKD offers its security is not based on the computational assumption. So now that we understand the motivation behind QKD, let's take a closer look at how it actually works. There are several protocols, QKD protocols we're going to look through. First one is prepare and measured protocols. These protocols rely on preparing quantum states and measuring them to establish a shared key. There are two main categories under this approach. First one is discrete variable QKD. In DV-QKD, photons are typically generated using weak coherent source like laser or a true single photon source. Its security is based on the non-cloning theorem, meaning that eavesdropper cannot copy quantum states without introducing detectable errors. The most well-known DV-QKD protocols include BB84 variants and DPS and COW protocols. Secondly, we have continuous variable QKD. Unlike DV-QKD, CV-QKD does not use discrete single photons, but instead encodes information in the quadrature components, amplitude and phase of an electromagnetic field. Security in CVQKD is guaranteed by quantum uncertainty in continuous variables. Some key approaches include Gaussian modulated coherent states and squeeze states. And other than PNM protocols, we have entanglement-based QKD as well. This type of QKD uses entangled photon pairs as the basis for secure key generation. By performing measurements on their respective photons, Alice and Bob can generate correlated results, which are used to establish a secure key. The most famous entanglement-based protocols include E91 and BBM92 protocols. We can also categorize QKD based on the channel. As you could assume at the first slide, we are going to use long optical fiber as our channel, so we will be focusing on wired QKD. So for this presentation, we will mainly discuss protocols on the left side of the slide. However, protocols on the right side, such as entanglement-based QKD and continuous variable QKD, are also fascinating topics. So if I get the opportunity in the future, I would love to give a presentation exploring free space QKD as well. This is the block diagram of QKD system, and to practically implement this system, we actually need more devices. So here you can see what the experimental setup actually will look like. For the light source, we can either use a laser diode or a single photon source. Since we're assuming a phase-based QKD system using a laser, we need to operate laser in gain switching mode. To do this, we require RF signal generator that produces pulses and power supply to drive the laser. Next, we have the modulator. If you're using a phase modulator, it also needs RF signal generator to apply a voltage known as V pi to shift the phase by phi radius. One critical issue with optical fiber is that they are highly sensitive to temperature fluctuation. So we also need this temperature controller to maintain stability. Other components in this setup may include interferometers or polarization controllers, circulators, or various other optical devices. The exact configuration depends on what QKD system you're using, so it really varies. And on the receiver side, the setup is almost identical to the transmitter with one key difference, the detector. Since we're usually using the single attenuated laser down to the single photon level, a highly efficient photon detector is essential for accurate results. So we're using SPAD and SNSPD for the QKD experiments. But being said, one of the biggest challenge in commercializing QKD system is because of these detectors. They are extremely expensive. So if you're interested, I would highly recommend to looking to them further, as they're really fun topics as well. Now let's go over how the BB84 protocol works using this example. BB84 is based on the idea that quantum states cannot be measured without disturbing them. It uses two bases, the rectilinear basis and diagonal basis, where each photon carry a bit of information. So when we first look at the quantum transmission, Alice first generates random beats, which she wants to send to Bob. She then randomly chooses a basis for encoding each beat and send the corresponding photon. And Bob, without knowing what Alice really sent, like what basis Alice used, Bob also randomly picks a basis for each measurement. Since he sometimes picks the wrong basis, he won't always get the correct beat values. So if we look at the example for the sixth part here, so Ellie sent the beat of 1 with rectilinear basis, but Bob gets the diagonal basis, which he has the possibility of getting either 0 or 1, but in this case, he gets 0. But we don't really need to worry about this case because after public discussion, the case where Alice and Bob selected different bases will be discarded. So yeah, that's all for the quantum transmission. And through classical communication, Alice and Bob compare their chosen bases and discard any cases where their bases do not match. This ensures that only correctly transmitted bits are used in the final key. So yeah, let's take a look at when Eve might be interfering. After transmitting their information of bases and discarding ones, to check the potential eavesdropping, Bob randomly reveals some of the key bits, and Alice verifies that they match her own. If there are too many errors appear, they assume eavesdropper might be interfering. Since the final key would be very long, even small disturbance caused by Eve would introduce detectable errors. This means that Eve's presence cannot be unnoticed. So that's how they keep this system secure. Yeah, the outcome could be the key, secured key. Through QKD using polarization states is easy to understand. It is not that suitable for fiber transmission because the polarization state is not maintained because of the birefringence of optical fiber. So in most cases, we use phase information rather than polarization states. So here's the basic general form of phase modulation. But I think only knowing BPSK is enough for later understanding. So if you look at this example here, it basically means if you have bit 1, then you get radius phi shift, phase shift. So if you compare this 0 bit and 1 bit, then you can see they have the difference of phi, phase difference of phi. And this is important in QKD because at the receiver, we measure the interference between pulses to extract the key. If two identical phase pulses overlap, like if the 0 pulse and 0 pulse overlap each other, they produce constructive interference and reinforce each other. On the other hand, if the 0 shift pulse and the 1 shift, phi shift pulse interact each other, they will have the destructive interference, which will cancel out the signal. This interference principle is crucial in protocol we will look through, where detecting interference patterns allows Bob to extract the secret key. So this is the basic figure for phase-based BB84 protocol. We should focus on delay loop and phase modulator, which plays an important role in this system. Just like the polarization-based BB84 protocol, the phase-based BB84 also defines two bases, basis 1 and basis 2. And state 0 for basis 1 corresponds to 0, 0, phase of 0, 0. And state 1, state 0 of basis 1 will be 0, 0. And state 1 of basis 1 corresponds to phi 0. And for basis 2, state 0 corresponds to pi over 2 and 0. State 1 corresponds to 3 pi over 2 and 0. Here we encode information by modulating the pulse, modulating the delayed one, which is separated from the beam splitter over here. Since the separated pulses originate from the same initial pulse, they retain the same phase reference. This means that even though the absolute phase fluctuates as light propagates through the fiber, the relative phase difference remains unchanged. So to create state 1, we apply a voltage of V pi to the phase modulator, which induces pi phase shift. Essentially, in this protocol, phase modulation itself determines the basis selection. After transmission to the quantum channel, so there's two poles. One is 0 and one is the modulated phased pulse. Bob also has the delayed line interferometers and phase modulator. By interfering the delayed pulses in constructively and destructively, he can extract the bit information. For example, when Ellis sends state 0 at basis 1, and Bob also selects basis 1, then this pulse would be 0, 0, so 0, 0. And since the Bob also selected basis 1, this also remains to 0, 0 and 0, 0. If these two pulses meet at the constructive port, they will reinforce each other, having a big pulse in the middle. But if it goes to the destructive destructive port, it will cancel out each other and have nothing on the middle. So that's how we can know which bits are sent. Other than that, it's basically same as polarization-based BB84. So the main difference is that the bit values are determined by phase difference instead of the polarization states, but the process of publicly relieving bases and calculating the error rates remain exactly the same. This slide shows the experimental result from the reference paper. They define each four state like this. And looking, they define four state like this. So this could be the result. And looking at the real experimental result graph, we can see that constructive interference occurs at photodetector 1 is interpreted as plus state, as they have defined here, plus state. And if this constructive relation occurs at the photodetector 2, then it could be considered as minus state. The second protocol we're going to look through is DPS protocol. It's differential phase shift, QKD. Unlike BB84, which requires basis selection, DPS uses a single measurement basis and encodes information in the phase difference between consecutive pulses. So if the pulse difference is 0, then it could be considered as bit 0, and the phase difference is pi, it could be considered as bit 1. And Bob receives the pulses and passes them through the interferometers. This means that each incoming pulse is interfered with the previous pulse before being measured at two detectors. The detector result tells Bob the phase difference between the pulses. For example, if constructive interference occurs at detector 1, the phase difference was 0, and the Bob records a beat 0. If the constructive interference occurs at detector 2, the phase difference should be pi, and so that Bob records a bit 1. One of the key security features of DPS is that if attempting to measure the phase information will introduce errors. Since the bit information is encoded in relative phase differences, measuring an individual pulses does not reveal any useful information. Instead, Eve's interference disturbs the interference patterns of adjacent pulses, increasing the bit error rate and allowing Alice and Bob to detect her presence. DPS is considered to be simpler alternative to BB84 as it does not require basis reconciliation. However, it is generally less secure than BB84 because its security proof relies on more specific attack models. But yeah, despite this, DPS is also used in high loss channel and it performs well in the conditions where photon loss is significant. This is the mathematical representation of DPS protocol. In over here, this is the J state, and this is the state of J plus 1. And yeah, phi means the phase of the pulse, and alpha is the amplitude. And after the interferometers, it becomes like this. This means that in detector 1, it would look for the constructive relationship. And for detector 2, it will look for the destructive ones. Lastly, we're gonna look through coherent one-way protocol. So how it works, the Alice sends a sequence of pulses, which are each logical bit 0 or 1 is encoded in the pair of pulses. Yeah, in this protocol, bit is encoded in the emptiness. So we can see over here, a bit 0 is represented as mu 0. This 0 means that the first pulse has a photon inside, and the second pulse is empty. Same for the bit 1. It's represented as 0 mu, meaning that first pulse is empty, while second pulse has the photon in it. In addition to these data pulses, Alice randomly inserts decoy sequence as well. It is represented as mu mu, or it could be 0 0 as well. So how it works, Bob receives these pulses and measures the time of arrival at the data detector DT over here. So the time slot works really important in this protocol. This data detector allows him to determine which time slot contains actual data bits, but he does not yet need to know if it is 0 or 1. However, Bob also has the monitoring detectors DM1, M2 over here that checks the interference patterns between successive pulses. These help detect any tampering by eavesdropper. Bob, same as BB84 protocol, Bob does not need to reveal the bit values. Instead, he only tells Alice the position where he detected photons. For example, if Bob detects photon at the time slot, position at 1, 2, 4, 5, 7, or 11, he reports this to Alice. Alice then reveals the position of the decoy sequence. So when this are sent. So if the decoy positions were 3, 8, and 10, Bob now knows which detected pulses were part of the decoy sequences. Bob then checks the coherence of these decoy decoy pulses using his monitoring detectors. If Eve tried to interrupt and measure the pulses, she would break the coherence between these pulses, disturbing the interference patterns. So if the visibility of these decoy pulses is lower than expected, Alice and Bob assume Eve is present and discard the key they made. So unlike BB84, Tau protocol does not rely on basis selection, but instead uses quantum coherence and time of arrival detection for security. Since Eve's presence would disrupt the coherence of decoy sequences, Alice and Bob can detect eavesdropping and discard the key if needed. This protocol has been successfully used for long-distance fiber-based QKD and hold the record for one of the longest QKD transmissions. So yeah, this is the experimental setup used for implementing Cow protocol in the paper I read. It is saying that they have improvement demonstrated in this setup is sharpened finite key security analysis, which optimizes performance for even the small box sizes. Most importantly, this experiment proves that long-distance practical QKD is feasible, even when they have standard telecom components. So yeah, now let's summarize the key QKD protocols. 3 of them, BB84, DPS, and COW. BB84 is the most well-established and widely used QKD protocol. Its strong theoretical security comes from using 2 non-orthogonal bases, allowing for eavesdropping detection. It is also hardware feasible, especially with advances in single photon detectors and decoy state techniques. However, BB84 has photon loss issues and is vulnerable to detector-side attacks. Despite those challenges, BB84 is the most commercially viable QKD protocol. And DPS simplifies implementation by using phase modulation instead of basis selection, making it more stable in fiber networks. And it is also it performs well in the high loss channels since it does not really rely on the true single photon transmission. However, its security is weaker than BB84 as it lacks basis randomness and is susceptible to coherent attacks. It also requires high phase stability, making it sensitive to environmental changes. While feasible, DPS is less widely adopted due to these security concerns. Lastly, Tau protocol is known for the simple implementation and stability, as it does not require maintaining phase coherence since it encodes beat by emptiness. It is excellent for long-distance QKD with a record-breaking 307 kilometer transmission shift. However, its security is only proven against collective attacks, and eavesdropping detection is limited compared to BB84. And it relies on visibility measurements, which require highly stable equipment. Despite these drawbacks, Coral remains one of the most practical QKD protocols for long-distance fiber networks. And this is just an additional slide to briefly highlight what I think could be some key future research areas for the practical implementation of QKD, but I will skip this part since we're running out of time, but please feel free to review it later. These are the research papers I referenced for this presentation. If you would like to explore any of the protocols in more detail, I highly recommend checking them out. But in the hindsight, I might have been better to focus on a single paper and dive deeper into one specific topic. But as I was preparing for the presentation, I kept expanding my research to understand multiple protocols, which led to somewhat shallower coverage than I initially intended. I apologize if the presentation felt so a bit surface level. Yeah. But if I have the opportunity to present again in the future, I would love to take more in-depth approach, focusing on a single topic to explore it greater in a greater details. So thank you for listening.
Thanks for the great talk. And if there's any question, you may ask freely. I think there's one question on the chat.
I'm sorry, just I'm suffering. Where did my Zoom? Oh, here. Why cow is the most used one for practical implementation? Um, it's because like I would say it really depends because BB84 is also known as the like most used one for practical implementation. But as far as I know, for the if you want to use it in the long optical fiber, then Cow protocol, they don't need to stabilize the phase information. So that's why it has the advantage of it. But for the secure system, because BB84 has two basis selection at the transmitter and at the receiver that has the randomness, it's more used for the secure systems. Is that enough for your questions? All right. It seems like the BB84 and CAL protocols only work properly when a single photon is emitted correctly from the photon source. Is that correct? It appears that a mean photon number less than 1 is used. How can we determine when a single photon has been successfully emitted from the photon source? Great question. For the BB84 protocol and CAL protocol, because getting a single photon is really hard, we are using the attenuated laser source. But theoretically, it's best to use the single photon source. Yes, and to know when a single photon, I think it could be known as if you measure it by photodetector or if you measure the intensity of it, but I'm quite not sure about it. Yeah, I think I need to look up for it more. Thank you. Is there any more questions?
Thank you for your answers. And why don't we just wait until 8 or 10, 8:10?
All right.
Okay, there seems no further question. Thanks again to Juhyun for the great talk.